So I got the code. I got the code from the team, from the authors of the paper, and I wanted to basically use the time now to take a look at it and then see how much this differs from what I was doing, right? So, and basically, this is my implementation. Yeah, exactly. God, I'll have to. It's been some days now. Uh, I'll have to refresh my mind on this. And I think this is the one that they sent for the paper in Archive. Okay, for the Maxcat problem. So, and this is also the 4, is it the 4 qubit? Yeah, so that's also the K14, I guess. And it seems like they've, I just, I'd taken a quick look at these, but there's so much in here, but it seems those are the results. Okay, there's gonna be quite some stuff to go through here. I think that's it, right? Because the rest, they also shared this one, but this is what is this code? I think that's a cleaner one, is it? Oh no, that's a more like a tutorial one. Okay, I see the. Mm, there's the titles in here. So they show the transpiled circuit. Okay. It's not that it's useful to us, I guess, right now, but with RTOF IX, but I guess it's the same, is it? So anyway, this is K14. So I don't know which one I should choose. Qubit mapping. So how do they do this? So qubit mapping, kit and physical qubit mapping with IBM Böblingen. Cal mapping. Physical qubit mapping on IBM Q Valencia. Okay. Retrieve. So this looks like they do some heavy executions in here because they do a lot of jobs and they are then pulling all the jobs somehow, plotting the results. Okay, so here we got some results. I see that also doesn't look so okay. So it also kind of doesn't look so good on the. Like you see the red ones or pink ones or whatever the color this is. It's the real machine. That's also because this is my. And I was wondering why this does not. This looks like shit to me. I mean, you look at the green ones. Like, look at the green ones, really. Okay. But that's with this bubbling machine. Readout error mitigated. KL divergence, I don't know. Okay. So with this, and do they, here Valencia. Okay, let's take a look at Valencia. So with bubbling, as you can see, doesn't really work well. And like not at all. The two solutions to these are like the solution to this would be one like all ones in here. And okay. And so and with Valencia, let's see. Let's try to look for the details. No, for the details for the results. Simulator results. Oh, well, so it's there. So with Valencia looks better. Now I can't access Valencia if I remember well. If I go, can I just go? Can I just? How can I zoom in and out? Reset. If I go back to I need to get the provider backends. If I execute this part, does this give me the backends? I ain't got a really good connection today. So there's that, but it doesn't print me the. But I think I can get so the IBM Q. It's quantum computing. I just wanted to at least try with the same machine, but this is probably not available for me. So yeah, so we're bad luck here. But we could try the other ones, but I see already that it doesn't have to really work, right? I mean, you see the machine here doesn't really. Yeah, I just wanted to let's then spend the rest of the video taking a look at the code and comparing, sort of comparing notes. See if the stuff that the way that I've been building it is anyhow similar to the way this has been building here. And I think I think there should be. They followed a bit of a different approach, I see, because they followed an approach where they created functions that basically generate portions of the circuit, whereas I have kind of like created the different parts of the circuit and then turned them into instructions, which kind of leads to this ugly thing here, right? Which kind of doesn't allow you to see the full picture together. Because I could turn those things into functions that they just return that portion of the circuit, and I think that's that. But yeah, well, let's I don't know if I with which file should I? I'll just stay with this. Seems we can take a look at both. Doesn't really matter. So let's take a look at the different gates. See, subdivided oracle. So this subdivided oracle, R Toffolies. So that's the oracle. Toffoli gate with one swap. Device topology optimal. Multi-control X. So they do. I gotta. CNX. I gotta see what that generates. But it seems like it's the algorithm in the paper where they do actually uncompute. This is the uncomputing part. That's something that I don't do. And then optimal diffusion operator. Circuit Hadamard, then multi-control X, CNX, and then Hadamard. So this is building the diffusion operator, and then the subdivided Grover method basically does, and it initializes the circuit, it adds the oracle, and adds diffusion. But it does this only once. And do we do it once? No, we do it multiple times. Okay. Okay, but let's take a look at it. Subdivided phase. So I guess this is the part that says, so what does it say? If angle equals 0 for the in range number of data. Okay, circuit RZ. So it adds. So this is the part that. So I'm gonna try to do it this way. It's not. That's not gonna be. That's not good. Let's go back here. So I'll choose the full screen. That is the first. That is the part that initializes the circuit. That's the. That is my. These ones. Yeah. So there's this theta times pi, and then they go and they say if angle is 0, then they do RZ rotations of pi over the number of data. And I guess if they give it an angle, they just do the angle times pi. This is for setting up the optimal. Okay. Art of M, Art of M, and Art of IX. Art of M. So the Art of M in my case, I use U2 gates. They use RI gates. Yeah, I don't know why I went with the U1 with the U2 and the U1 gates, honestly. But it's the same idea: RICX, RICX, RICX. And then these are both positive pi over 4, and these are negative pi over 4. Yeah, and then the T is the target. So here they pass the qubits. Okay, that's reference. And Toffoli IX. I guess that's my RTOF. I think this is the one. Yeah. But because wait a second, I have Hadamarts here and they don't. Why don't they have Hadamarts? Okay, so instead of a Hadamard and a T, instead of Hadamarts and T's, they've replaced that with a U2 rotation. Let me check the paper. It was Grover, Nisk. So they've replaced the Hadamard and the T gate by this U2 rotation, which should be equivalent. I'm assuming. But I just want to see if this is something that's mentioned in here or not. No, but it's instead of these HD, it's these H Hadamard and it's Hadamard and T gates and the T dagger and Hadamard gates. Okay. And here they do the other one that's equivalent to the T dagger and the Hadamard gate. So this would be something to take a look at, whether this is equivalent or not, but it probably is. See, I'm lacking some nice how could I see this? So what if I create a new It's a new Python 3 notebook. I just gotta get better at in general. So what if I'll basically I'll create like one circuit with one qubit, and I'll create another quantum circuit with another qubit, and to C I will add basically a Hadamard gate, and followed the T gate, and Q1 is going to be a U2 rotation. That is going to be this one. But T is going to be 1. And now I want to basically so Qiskit visualize block sphere. I just plot block vector or something like that. Yeah, no plot. Plot block vector. I wanna title size. No, that's the block vector. I want to plot the block. I want to plot a qubit. I did that and I forgot how to do it. Qiskit, not do that. I first need to actually run both through a the state vector simulator. So basically, get them, and I haven't touched that for a couple of days, and I'm already lost. How can I get the simulator? How do I get the simulator here? Getting the simulator. State, but I'll look at the state vector simulator. And then was it execute C simulator 1,000 times? Execute Q simulator 1,000 times. Was it something like this? Simulator shots. So I gotta say shots in here. Shots. Have it down. Out of range. Oh, sorry. Keep it 0. Keep it 0. It's of course not pi. It's np.pi. Oh no. Pi is not defined. That's why I say np.pi. How's pi not defined? How's pi not defined? Okay. And now I wanted to Qiskit state vector simulator. plot the blocks here. That's what I want. I find it difficult to remember this, but it's me, I guess. What? That's the source code. I don't want a source code. Qiskit elements. No. What? Documentation. Oh, that's the. Oh, okay. Here. Measure. No. Backend. Get. Aha. Okay. Should get the results actually. And then you get it the state vector, and that should just plot block multivector. That should just do it. So basically, so job C is going to be C, and this is going to be job Q. So we're going to get rid of these, and then we're going to do a C, and we're going to do another plot with Q. So from the job, you get the state vector of a given circuit. So you have to give it this circuit. Why do you have to give it the circuit? Okay. So that's Q. Did it just get overwritten? Do I just have to do this? C. Yeah, so that's the same. That seems to be roughly the same. Okay. And if I now add to the circuits the what was that? T-Dagger and Hadamard, or versus these. So now I will say what did I for example, for Q is why I use the U2, right? So Q, for Q I add these, and now I kind of and for C we basically add a T-Dagger and a Hadamard. T is not defined, yeah, because that's 0. So, oh, but I hope I now don't have twice the T-Dagger. Let me just do that again. So I'll just do that because I think that might have added the T-Dagger and the Hadamard gates twice. Okay, now. And now I basically go through these again. And we're back at 0. And throw these again. Where is... Here, I kind of lost an Excel. And I do this, and we're also back at 0. So those things work. I gotta get used to. I mean, it's not that I gotta get used to, but yeah. So whatever, that's okay. Those are equivalent. Toffoli swap. So where I was. So okay. So this is basically this. Our Toffoli IX U2. So what I did here is for the RTOF, which is the IX is Hadamard T, and then T-Dagger Hadamard. Those are the two things in here, and then CXT TDG CX, right? CX, TCX, TCX, TCX. Yeah, it's the same. Now the quantum, so okay, so now let's take a look at the Toffoli swap. So now I did a trick here. I did a trick here where I added that second swap at the end to correct that already within the operation. So I don't have to change whatever comes next in the circuit. Toffoli swap. So C1, C2, T, that takes you to C1, T, C2. So now it's going to be complicated to check because this means they've basically swapped the rest of the circuit after that. But that's why I don't see. That's why I'm thinking why can't we just swap it back right after this? It just then it leaves the contract of that function sort of the same. Device topology. Okay, so but this is, let's take a look at this. So we've got a Hadamard CX and TDG. Hadamard CX and TDG. So I'd love to compare these side by side, honestly. Why doesn't this? Okay, yeah, it's gonna be. So we've got these. This seems to be the same. Seems to be the same. I add a barrier here. Okay. This doesn't seem to be the same. Let me paint that circuit. That's going to be easier to compare. So it's going to be easy to compare. So if I take a look at these, if I do this, and I go, so this is just I'm playing here with stuff. So I'm going to create a circuit equals quantum circuit. So this is going to have 3 qubits, right? 3 qubits. And I'm going to basically, I'll call it basically QC. Easier if I just copy I copy this as a function. It's going to be easier for me. So I copy this as a function. And now I do QC equals quantum circuit 3, and I do basically what I will do now is I'll just call the function with this circuit, and it'll say control 1. I guess this is 0, 1, or 2, right? Okay, and now if I do QC draw output MPL, should draw me something nice. Now let's compare. Okay, so okay, some actually quite some differences in here. And it could be on my side. So this could be where things go south. This part should be equivalent. So let me just zoom in here, zoom in here. So no, I'll zoom out because I cannot use the drawing tools. So up to this part, it should be equivalent. Then we've got this T. Then we've got this T in here, which wow, which I don't have. Okay. Okay, so now is this the could it be that there is a mistake here on the paper, that this is the same? So if I take this to the other side, and because I mentioned that I thought this has a yeah. No, this is because I mentioned I thought there was a problem, but I essentially have stuff here. I also have this part in my circuit flipped, which is not good. Now, but how could we test these? So how could we test these circuits? So basically, the way we should test the circuits is by maybe running them on a simulator, right? So now I've got QC that generates this function. I'm gonna now create so I'm gonna add another swap at the end just to keep the consistency, just to keep the controls and targets in order. Okay. So we've got this last swap at the end. Now I will basically, can I remove that? Okay. Now I'll basically take my, what did I do? Cancel. I'll take my stuff in here. And I'll make another function. I'll call it, so we'll call it the same, but we'll call it hopefully swap. Intuition. And I'm basically gonna copy that over. Because I'm lazy, I'm gonna call this, I'm gonna rename it here. And now I gotta basically, so everywhere that says 2 should say target. Target, 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 and then the rest should just say control. So it's control. But control 1, sorry. So ones are basically, the zeros are basically control 1. Control 1, control 1, and ones are basically control 2s. Control 2s, control 2s. So what I want to do is I want to basically, now that I've got that, I want to do QC intuition is equal quantum circuit. Circuit with 3. Now I will basically apply these to QC intuition 0, 1, 2. What's wrong? Target. Perfect. I just called all my targets target. Target, 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 target. And I can also now take a look. What have I done here? Take a look and do draw output equals NPL. So here we have it, and it's exactly the same circuit. So now we've got QC intuition and QC, right? So if I now do QC and draw output equals, now we want to test these by so wrong. A second. First, we'll do. So I want to apply. The way I want to test is I want to apply a QC Hadamard 012. I got the 3 Hadamards. I got a starting superposition, and then I'm testing the Toffoli on the superposition and see and we should get then see what outputs we get, and then here here I want to do the same. So I want to do Hadamard 012. Exactly. Okay, so we got this now, and then I want to run those 2 circuits in a simulator and output the and plot the histogram. Plot the histograms. And we should only get results which are a valid subset of inputs and outputs for the Toffoli gain. So we've got the simulator. So I guess we're just going to copy that. The one is going to be QC. The other one is going to be QC intuition. So I'm going to call this like that, QC intuition. And I'm going to run the jobs. QC intuition is not defined. Intuition, of course, that's the name of the circuit. We should try. Oh my god. QC intuition. QC intuition. QC intuition. So I should try to not keep the typos, fix them where they are. Okay, so we got this, and now I basically want to plot histogram. Plot histogram of QC. Oh, how does a plot histogram work? Not this way. BMQ plot histogram. Actually, I have it probably here somewhere. Get counts. I need to get the histogram. To get the counts first. First, I need to get the results. That's the first thing. Okay, so I got the results already, and then I just need to do top QC get counts. I think that's the way it works. I get counts, and that's the and I can plot them all together. That would be nice. Okay, so actually, it's WQC counts, WQC intuition counts. Let's see what happens. Okay, they both work. Interesting. They both give me the same result. It's a nice way to compare that, though. But that's not. Well, maybe I should measure. Maybe I should add a measurement operation. Oh God. Yeah, that's what happens. So Q should be 3. I should basically say measure. Does it work like that as well? Or do I have to specify QC measure? Specify this. Yeah. Okay. And here, kind of basically the same. And now basically at the measure at the end without the QC if possible. And circuit's not quantum circuit. And intuition. Oh, come on. Measure. I'm just blind. Okay. I do the measures. The measures. Jobs. Results. And now I plot the stuff. And essentially, that's weird. That's weird. Because I should be getting so I should be getting all the possible combinations, right? Like if I have a layer of Hadamard's here. Oh, sorry. I know what happens. That shouldn't be here. It should be just for the inputs. Just for the inputs. Okay. So this we go. No, still. Just one Hadamard in qubit 0 and 1. Oh yeah, okay. So this is the first Hadamard in there. Yeah. So this is correct. And then here also, I want to get rid of this Hadamard. Yeah, so I need to get rid of one Hadamard because I want to do a Hadamard on the inputs only. And then see what's the outcome. So, oh, that doesn't work either. Why? Damn it. That's what I expected. What I want to do is these, right? So if I start here and I go into superposition and I do it damn toughly, you see that the probabilities of, I want to get those probabilities, just different amplitudes, right? But I'm not getting them somehow. That's what's, maybe because I just run it, maybe I should just shots 1024. It's the amount of the shots. Just in case. It's not amount of the shots. It counts. So if I do it is really the only stuff that's in there that counts. That is awkward. And for these as well, right? Why? Those things, especially on the simulator, should work fairly well, actually. Okay, so I'll stop here for now. But basically, I have to figure this out. I definitely have to figure this out. It's there is a difference of implementation in here, so this might be one of the reasons things don't work. I just want to make sure that I can compare them. Even if I compare them like that, which they should give me the same result, they don't. So, but it's not giving me the result that I expect. That's basically that kind of distribution, right? I want to get all these different elements in there with equal probability. That's what I'm looking for. Basically, these. It's as simple as this. Cool, but I'll save that and then I'll go back to these later. Because now it's basically time for the live session already, right? In 5 minutes, it's cool. Come on, a couple more minutes. A couple more minutes. They should. Why doesn't this work? Why doesn't this work? I just don't get it. I start with a Hadamard. QC intuition on the simulator. Maybe. I mean, that's not. That should be okay. Why doesn't this work? Let's do one last stupid try, okay? Basically, I'll call the quantum circuit like T. Quantum circuit 3-3. I'm going to start with a Hadamard and keep it 0 and 1. Then for T, I'm going to add the control X 0, 1, 2. I'm going to draw. Sorry, I'm going to measure. 1, 2. 0, 2. And I'm going to draw. Not good. MPL. You have it. And now I'm going to basically run a job in the simulator, and job T. Then I'm going to plot it. Plot histogram. Plot histogram of job counts 001. So none of these. Awesome. Really? What am I missing in here? What am I missing? Why I don't see if this is the I should be seeing I should be seeing these 25%. No. Yeah, I should be seeing each of these possibilities 25% of the time. I'm doing something wrong. Cool. I'll stop here because I ain't got much time now. But I'm definitely doing something wrong. But I think the idea of testing it like that is not bad. Save as TOEFL test. Cool. Cool, 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 cool. So Twitter Studio.